Welcome to The Explainer. Sometimes you run into these physics problems that just seem impossible. And today, we're going to tackle one of those classics from the Irodov collection, the falling chain problem. We'll solve it step by step, and more importantly, we're going to uncover a really powerful problem-solving method you can use anywhere.
So here it is, problem 1.184. It sounds pretty simple, right? You've got a chain, partly in a tube, partly hanging out. You let it go. How fast is it moving right at the moment the last bit slips out? The question is simple, but the solution? Well, the solution reveals a really elegant and beautiful physics principle.
I know. When you first see it, it looks a little intimidating with all the variables, but our goal today isn't just to get to the answer. It's to master a strategy, a way of thinking that makes even complex mechanics problems like this one much more manageable.
So, here's how we're going to break this down. First, we'll pick our tool. Then we'll look at the chain right at the start and then right at the end. After that, we'll put it all together to find the velocity. And finally, we'll talk about the big takeaway you can use for all sorts of other problems.
Okay, let's dive into this. The first, and honestly maybe the most important step in any physics problem, is picking the right tool for the job. Seriously, it's like choosing between a sledgehammer and a scalpel. One makes a huge mess, the other gets the job done cleanly and delicately.
We've got a couple of options here. We could try using forces. Newton's second law, F equals ma. But that gets messy fast. Why? Well, think about it. As more and more of that chain slips over the edge, the weight pulling it down keeps increasing. That means the force isn't constant. And if the force isn't constant, the acceleration isn't constant either. That leads you down a dark path of messy calculus. But there's a much better way, conservation of energy. This approach lets us completely ignore all the messy details in the middle and just compare the very beginning to the very end. The magic word in this problem is smooth. Whenever you see that in a physics problem, it's a huge hint. It's code for, hey, you can ignore friction. And if there's no friction, well, that means no energy is being lost from the system. The total mechanical energy, that's the kinetic energy plus the potential energy, has to stay the same. Whatever you start with, you have to end with.
All right, so let's put that powerful idea into practice. We're going to start by figuring out the total energy of the chain right at the beginning, at the exact moment before we let it go.
So here's our starting lineup. We've got a length of the chain just hanging there. Now, to talk about potential energy, we always need a reference point, a 0 point. The easiest, most convenient place to put it is right at the level of the tube. So we'll just say anything at this height has 0 potential energy.
Okay, let's get into the numbers for this initial state. First up, kinetic energy, the energy of motion. Well, the chain is just sitting there, right? It starts from rest. So kinetic energy, 0. Boom, done. Easy part. Now the potential energy. Only the part of the chain that's hanging has potential energy relative to our 0 line. Let's find its mass. If the whole chain has mass m over a total length L, then the mass of the hanging piece is m over L times h. Now this is a key trick. For a uniform object like a chain, we can pretend all its mass is concentrated at its center of mass. For that hanging piece of length h, the center of mass is right in the middle, at a depth of h over 2. Since it's below our 0 line, we call that a height of negative h over 2. So we plug it all into our formula. Mass mh over L times g times height negative h over 2. Multiply that all out, and you get negative mgh squared over 2L.
Perfect. We've got our starting energy locked in. Now, let's hit the fast forward button. We're jumping all the way to the end of the action, the exact instant that last little link of the chain is slipping out of the tube.
So here's what it looks like at the end. The entire chain, all of length L, is now hanging straight down. And it's not just hanging there, it's moving. The whole thing has a downward velocity, which we'll just call v. And that v is exactly what we're trying to find.
So we're going to run the same playbook for this final state. First, kinetic energy. This time, the whole chain of mass m is moving with velocity v, so that's a classic 1/2 mv squared. Now for potential energy. The entire chain is hanging down. Its center of mass is now halfway down the total length, so it's at a depth of L over 2. Again, it's below our 0 line, so its height is minus L over 2. The potential energy is then its total mass m times g times that height. That gives us minus mgL over 2. And there we have it. We've done the heavy lifting. The physics part is basically done. We know the energy at the start, and we know the energy at the end. Now comes the fun part. We just set them equal to each other and let the algebra do its magic.
Okay, let's walk through this. Step 1. The law says initial energy equals final energy. So we write that down. Step 2. We plug in those expressions we just worked so hard to find. Now step 3 is where it gets satisfying. Look at this equation.
every single term has a mass m in it, so we can just divide the whole thing by m. Poof, it's gone. We can also multiply everything by 2 to get rid of those fractions. That cleans things up nicely. That leaves us with negative gh, h squared over L equals v squared minus gl. Step 4. We just need to get v squared all by itself, so we add gl to both sides. And finally, step 5. We can pull out the g just to make it look a little neater.
And for the grand finale, we just take the square root of both sides. And there you have it. The final velocity v is the square root of g times the quantity L minus h squared over L. That's our answer. We did it. Look, getting the right answer is awesome, but that's not the real prize here. The real takeaway is the method. Understanding this strategy, that's the tool you're going to use to crush other problems that look just as scary as this one did. So, let's turn this into your problem-solving cheat sheet. First, always look for the simplest tool. Here, energy conservation saved us a ton of calculus. Second, be super clear about defining your start and finish states. Third, pick a zero level for potential energy and stick with it. Don't change it halfway through. Fourth, remember that center of mass trick for objects that are spread out. And maybe the biggest lesson of all, don't get psyched out by a scary-looking problem. Just take a breath and break it down into these manageable steps.
All right, I'll leave you with one last thing to chew on. What if that tube wasn't smooth? What if there was a little bit of friction? Friction is an energy thief. It steals mechanical energy from the system and turns it into heat. So how would you have to change that simple initial energy equals final energy equation to account for that lost energy? Give it some fact. Thanks for joining me for this explainer.